Okay, so all eyes up here, guys. All eyes up here. So we learned how to do the basics. All right. The last 3 days we spent just simplifying radicals, and so that's an important kind of component or foundational skill that we have to have in order to move on to other skills. Okay. So what we're going to do is we're going to look at how do I just add and subtract radicals. Okay, and what are we looking for when we do that? Okay, and I want you guys to think of this as similar to adding and subtracting monomials. You always add like terms, right? And so our goal, guys, is to add only radicals that have the exact same stuff under the radical. Okay, so what do I mean by that? Okay, whatever's under the radical, this stuff is called the radicand, by the way. That's called the radicand. Okay? So as long as both terms have the same exact radicand, they're both 7, then what you can actually do is just add their numbers out front. So you can kind of think of it as like groups of root 7s. Okay? So how many root 7s do I have then? 9 plus 4. Right? So what's 9 plus 4? 13. So my answer would be 13 root 7s. And a lot of students like this easier because it's really just adding the numbers out front of the radicals. As long as they're the same, you can just add them up. Okay? And so it's very similar to what we did with monomials, right? So if I had 2m plus 3m, how many m's do I have? 5, right? I have 5 m's. That's the same thing with radicals. If I have 9 root 7s plus 4 root 7s, then I have a total of 13 root 7s. So always think of it as whatever, as long as you're the same, you add the numbers out front. It becomes very easy to do. Okay? So can you guys tell me what this one would be? You see how I have the same stuff under the radical expressions, right? So how many root 5s do I have? Yeah, so negative 10 plus 2 is negative 8. Good job, Ken. So I got negative 8 root 5s. Yeah, because we got negative 10, you go up 2.
Okay, I was just looking at the minus sign, and I just thought it was subtraction.
So really, once you guys see, oh my gosh, this is just basically adding like terms, it's not too bad, all right, to start. Right? We got to see that to start, right? So like in this one, see I got 3 separate radicals? 3 separate radicals? So what I do is I just take the numbers out front and add them up. Or subtract, depending on what the sign is, right? So I have 6 root 15s here, minus 1 root 15s here, plus 1 root 15s here.
So when there's no number, you just put 1?
Yeah, you just put 1 in front.
Right.
Yeah, so all I do is just add their numbers out front. So what's 6 minus 1 plus 1?
7.
Yeah, 6 minus 1 is 5, right? And then 5 plus 1 is 6, right? So you can think of it as you're just left with 6 root 15. Another way to look at this is these two cancel. Right? You got a negative 1 root 15 plus a 1 root 15. They cancel. I'm just left with that. Okay? Okay, so a situation like this, though, you got to be careful because it looks like they're all the same, doesn't it? It looks like the stuff under the radicals are all the same. See, only this one and this one is the same. Okay? So what you got to do is just put your like stuff together. So I'm going to circle the 2 like terms. This and this. Those are my exact like terms. Okay? So how many root 2's do I have? What's 5 minus 4? So I got 1 root 2's. Okay? This thing, you just tack on at the end. Because you see how the radicand is not the same exact as those. Even though there's a 2 in there, the whole thing has to be the exact same in order for you to subtract the numbers out front. So all you do is just tack it on the end of the answer. So it'd be minus 3 root 2x. So it looks kind of ugly, right? The only things we could put together were these two expressions right here. And you just tack this other term on the end of it. Okay? So what we're going to do is we're going to extend that concept now to where you might not have common radicands, but you can still produce them. Okay? So let's look at some cases where that pops up. Okay? Alright, I'm adding two radical expressions. You guys see that? Okay. Are there the same numbers underneath both of those? No. So here's what you do. You got to pull out perfect squares out of each of them to find common radicands. Just like we did with simplifying radicals. Okay? So the question would be this. Okay? Is there a perfect square that comes out of 108? So look at that list I gave you. Okay? And I want you to be thinking about, okay, what perfect square, or what's the highest one I could take out of 108? The highest perfect square I can divide out of 108. So you could definitely, we'll try 4. Go ahead and take 108 divided by 4. Try that first, because that's one of our lowest ones, right? And what does that turn out to? Okay, so that one could work. Is there a higher one though? 9 comes out. And then what about higher than that?
11.
Oh, look at your perfect square list. 11's not a perfect square. Look at the bold numbers, right? So what about 16? 16 doesn't. What about 36? That's another higher one on that list. 36 and what? 3. So you see how that's probably the highest one. So if you pick the highest one, you make your life a lot easier to work with, guys. Okay? So you see how it's 36 and 3 make 108. All right? Now this left radical becomes 6 root 3. Okay? That's 6 root 3. So we'll keep that in mind. Now we're going to do the same thing with 75. What perfect square comes out of 75? 25 and what? 3. 25 times 3, right? So you do exactly what we did the last few days. You just simplify the radical. And here's what happens is kind of cool. What's root 25 become? 5. Can I do anything to root 3? No, so you just tack it on. Here's the beauty of what we have now. You see, now I have the same radicands, right? See how these are both root 3s? So now what I can do with their numbers out front? Add them. So how many root 3s do I have? 6 and 5 is 11. So I have 11 root 3s. Okay? That's our answer. So really, I always tell students, it's just more of an extension of what we studied, last few days, guys. Okay? So if you don't have a common radicand, you just want to split it up where you find a common radicand from the reduced form. Okay? So let's give you another example here. 3 separate radicals. Okay? So we're going back to some of our times facts. And this is important, right? What comes out of 63? 9 and what? 9 and 7. Very good. So I'm going to split that guy into 9 and 7. Okay? Okay, what perfect square comes out of 175? So it ends in a 5, so 125 probably comes out. So 25 and what? 7. Very good. Okay? And then let's look at that last one, 112. And I'll give you guys a little hint. When you break these down and you notice a common one in each of them, most likely that's going to come out of the last one too. So 7 should come out of 112. But you could check it. Let's look for perfect squares that come out of 112. 7 and what? 16. 16 is our perfect square. Okay? So all this is, guys, is doing exactly what we did the last 3 days. You just break a radical down to its lowest form, And what you're going to see is the first part becomes 3 root 7. Okay? What does this part become? 5 root 7. And what does this one become? 4 root 7. Very good. Okay? So how many root 7s do I have? 3 plus 5 plus 4. So, yep, 8 plus 4, that's 12. Very good. So that means I have a total of 12 root 7s. So I always tell students, when you add radicals, you just kind of break them down to get common radicands, and then add their numbers out front. Okay? So let's see where we're at. Let's look at number 7 together. Okay? And I want you guys to tell me, are these common radicands? The x is the same, right? But what about the numbers? They have to be the same to add the numbers out front. Okay? Just like common monomials, right? So what we got to do is split them up separately. Okay? All right, what's 28 split to? Close. 28 splits to what? Not 4. Well, 4. See, none of those are. Well, actually, 4 times 14 isn't 28, though, y'all. Be careful.
4 and 7.
4 and 7. Very good. So I would write this guy as root 4 times root 7, and then just put the x on the non-perfect square. You see how the x is in there? I'm just going to put it with the non-perfect square factor. Doesn't matter where it goes, I'm going to put it on this guy. Okay? Easy way to remember if you have something like that. All right, 63, we've seen that one before, right? What two factors go into 63? 9 and 7. So it's root 9 times root 7x. All right, so let's focus on one piece at a time here. What's this 4 become? 2 root 7x, right? And what's this root 9 become? 3 root 7x. So here's the beauty behind this. Look at, do I have the exact same radicands? So I have a total of 5 root 7x's. 5 root 7x's. Okay? And so you guys are really kind of extending that, what we learned the last few days there. Okay? Is there anything in common with these two? Okay, so but what about the radicands? Do you have common radicands? And then here's the problem with this one. Can I split 17 down? That's a prime number, right? What about 5? So you leave it. So you say, can't be simplified. Or in this case, you'd say, can't be simplified. Because I'd have no perfect squares that come out of either of those radicals. Okay? What about this one? 2 radical expressions. Can't take anything out of 3. But what about 100? Or 300, excuse me. So look at that list. Okay? What's the highest perfect square that comes out of 300? Right from that perfect square list. The highest perfect square. I'll give you a hint. It ends in a 0. So 100 comes out of it. Alright, that's kind of it's a number theory thing, right? So, yeah, I just write this guy as root 100 times root 3. Where 100s are a perfect square. That's the magic number that you want to put first. Very good. Okay? So, you see how I have 6 root 3 plus root 100 times root 3? Well, what's this really become? What's root 100? 10. So that's 10 root 3. So how many total root 3's do I have? You got 6 plus 10. How many total we have? 16 root 3s. Okay? 16. Go ahead and try number 10, please. Try that one on your own. I want to see if you can kind of break down the second one there, okay? See if you can get a common radicand to be able to add those up correctly, okay? Try it real quick. See where we're at. Okay? Remember, just put the B on the non-perfect square factor. Easy way to remember. Drag it down, put maybe 2 times 3. Okay. On this one, split to root 9 times root 3. Okay. They split it up to start. Go right from there. Good job, guys. I'm seeing some good steps. That's half the battle, it's just the thought process, okay? You'll get better at these. It's just a matter of looking for those perfect squares, okay? What number you're adding? -9 plus 9. Okay, so keep in mind when you split this up, these are radicals. Let's get rid of that. So that is 3. 9 is 3. Then you get another 2 plus 3 is positive. You got positive 1. So this becomes 3, right? And then that's 3 here. And that's 3 times 7. Right? So yeah, I'm seeing some good steps. That's awesome. I'm just going to jot a few things down here so you guys see it. But, you guys, did I do this first? Or did you guys do this first on the right one? Yeah. Because that's the only one that can be broken down. Okay? This, you can't do anything to. So I'm just going to kind of carry it down right here. Okay? So now you recognize that, hey, you know what? The square root of 9 is 3. Okay? And now I have the same exact radicands, 3b's under the radical. You guys see I got the same exact radicands? So all you have to do is add the numbers out front. So how many 3b's do I have? I got 1. So my answer would be 1 times root 3b. There's our answer. Okay? So we gotta look, remember, it's just breaking down to the lowest form. You'll always find a common radicand when you do that. It's kind of neat. Okay? Alright, look at this one with me here. Number 11. How many terms do I have? 3 terms. Okay? Which 2 are just like each other? So I'm going to circle the 2 that are just like each other. Why are those 2 just like each other? They what matches in them though? The radicand matches, the 2 m's. Okay? Very good. So all you do is put those together first. You could say, alright, well how many root 2 m's do I have? 4 minus 4? So that cancels. Those are gone. It's kind of like like terms canceling. So what am I left with? 6 root 3m. That's all I have. So that's a classic example of, hey, sometimes like terms cancel out. Okay? But in a situation like this, do I have like terms? I got m's, which is good. But what about the numbers? They're not the same. Okay, so our goal is to produce the same radicands. Okay, so to do that, we're going to split each of these up. Okay, all right, what comes out of 50? What perfect square comes out of 50? 25 and b. Very good. So you write root 25 times root 2m. And notice, where did I put the m at? On the perfect square or the non-perfect square? Yeah, just put it on the non-perfect square factor. Okay. All right. 72. What perfect square comes out of 72? 9 does. But see, you want it to match this one. You want it to have a 2 in there. So that's a little trick. You can divide out a 2 out of 72 and get 36, right? So you really should be using 36 times root 2m. Okay? So here's the beauty behind this. Look at, what's root 25? 5. The root 2m tacks on. Okay? Plus, what's root 36? 6 times root 2m, right? So here's what you guys see. Exact same radicands. So what do I do with these numbers out front? 11. How many do I have now? 11 root 2m's. Not so bad. So really, it's just, you see, it's an extension of what we've covered. Okay? All right. Take a look at this one. How many terms do I have to start with? 3. Okay? Are any of them the exact same? So we gotta do our strategy. Okay, let's split up each piece. Kind of like a little tree, right? Christmas tree method. Factor method. That's kind of what we think of as a Christmas tree. You just break it down to its parts, right? Okay, so 16. Well, we know that breaks down to what? That's 4, right? So you're going to get 4 times root z. Okay, so that's that first piece, is 4 root z. Okay? Plus, now let's focus on the second piece. Okay? What's 8 split to? 4 and 2. So don't forget this 2 out front. We're just going to carry it down out front right there. And that's going to be times root 4 times root 2z. Because 8z has got to split down into root 4 times 2z. Okay? And then we'll focus on our last piece. Can't do nothing to that. That's just right there. Okay? So let's just see where we're at here. Now we have, let's look at that middle part. The middle part's still kind of ugly. What's the square root of 4? 2. And what's 2 times 2 out front? So these two things really just become 4 out front times root 2z. So that middle piece is just that. Okay? So we're just going to copy everything just to make sure we have everything organized. And here's what you're going to see. Which two are the only ones that are like each other? The first one and last one, right? Why are those ones like each other? Because they have what under the radical? A z, right? You see how that one has a z, but it has a 2 in there also? So you can't add that one to the other ones. Okay? So all you do is you put your like stuff together. 4 minus 3. So that's 1 root z. And then you just add this guy to it. Plus 4 times root 2z. And your answer looks more as like a extended sum. Okay? So in that case, you just got to be careful in terms of really just combining only the like pieces. If it's not like, you just tack it on. Okay? Kind of like x squared plus x. Can you add those two together? Or combine those two together? No, because the exponents are different, right? So they're different identities. Exactly, exactly. Okay, so look at this, guys. Here's a good question for you guys. Okay, go from least to greatest in the order of these radicals. Sometimes this can be a little confusing at first because when students look at these, they say, "Wait a minute. 2 is smaller than 8, which is smaller than, so 50 is the big." We think but that's not always the case. So here's what I tell students to do. Just convert these to decimals. And then you can figure out smallest to biggest. And then we can look for some patterns from there, but a lot of times that's the easiest way to check. Okay? So do this on your calculator. We're going to take 3 root 8. Okay? Let's start with that first one. So you just type it in. 3, I don't know if that's a little blurry or not, but times the square root of 8, and I get 8.49. So that's 8.49. 4 times the square root of 2, that's 5.66. And then the root 50, the other one, the square root of 50 is 7.07. So now we can analyze their decimals and you know which one's bigger or smallest, right? Or they want to go from least to greatest. So which one's the smallest? 4 root 2. Which one's the next smallest? So root 50, right? And then which one's the largest? 3 times what? Root 8. And so are you guys seeing? I guess I don't see much of a pattern in with those numbers. So really, I would just do that, and it's really definitive. It's really trivial. You'll be able to see which one's bigger or smaller. Okay, and that just reminds students that hey, these can be expressed as decimals too if we wanted to in those cases. So every once in a while, you guys will see like on a map. Usually this happens in different scenarios, but not all the time, but they'll express their distances in that radical form. It's kind of weird, but you don't usually see that. But if you do, you know what they're talking about, right? And so they're saying, okay, shows the path of a delivery person, this map. And they're showing write the total distance that you traveled in simplified radical expression form. Okay? Well, let's say we started right here. This is our start point. And then we're going all the way around to where we started at. Kind of like a mail route, okay, or something like that, where you have different houses you're trying to drop off. Well, all you do is you add them up. So the total would be 3 miles plus 112 route 112 miles plus 2 miles plus 2 route 7 miles plus route 28 miles. Okay? And this becomes a situation where, hey, we could just add radicals if they're already in that form. Okay? Well, which ones are easier to add already? The 3 and 2. That makes what? 5. So let's put those together as 5. Okay? Now, the 3 that we got to focus on is this one, and this one. Those are your radical mile markers, right? So let's split them up. Let's start with 112. Let's start with that guy. We'll kind of split this guy like a tree right over here. Well, I think we've seen that one already today, right? What was our 2 magic numbers that made 112? Which one? Well, 6 and 7 doesn't make 112 though. So divide out those perfect squares out of it. What's the highest one that comes out of that thing? Yeah, it ends in an even number, so yep. 7 and 16. Now right now there, okay, bud. So 7 and 16. So it'll be 16 times 7. Very good. What's that guy you can't do nothing to, right? So that's just 2 root 7. So we're just going to leave it as 2 root 7. It's going to carry it down right there. Okay. And then what about 28? 4 and 7. Good job, Dalton. So now we have everything like we want, right? So what's 4 root 7 become? 2 root 7. So now we just put our like pieces together. How many root 7s? Well, this guy is really going to be what? That's 4 root 7, right? So let's put all our root 7s together. How many root 7s do I have? 2 plus 2 plus 4. So that's going to be what? 8, right? So we got 8 root 7s plus the 5, or 5 plus that. So that's your total distance in radical form. Okay? So kind of neat, just like using that kind of stuff.